Have you ever pressed a button on your calculator, sine, cosine, e to the x, and just trusted the answer that pops up? Well, today, we're going to pull back the curtain on the incredible mathematical machinery that's working behind that tiny screen. I mean, really think about it for a second. These aren't simple numbers. They have infinite non-repeating decimals. So how does a tiny little electronic chip figure out these incredibly complex values in, a fraction of a second? It honestly feels like magic, but I promise you, it's just pure mathematical genius at work. So the secret isn't that your calculator has some giant, impossible-to-store list of every possible answer. No way. The real secret is so much more elegant. It uses a powerful technique to get incredibly, mind-bogglingly close to the real answer using only the simplest math. And that trick? It's called approximation. Okay, so how does this trick actually work? Well, it all comes down to something you probably learned about in high school algebra, polynomials. Simple, predictable, and, as we're about to see, unbelievably powerful. So why polynomials? Well, for a computer, they're an absolute dream come true. Think about it. They only involve addition, subtraction, and multiplication. No weird, complex functions, just basic arithmetic that a computer can do at lightning speed. The whole idea is to use these simple building blocks to construct a near-perfect imitation of a much more complicated function. Now, I know the math on this slide looks a little intense, but the idea behind it is actually surprisingly simple. Imagine you had to draw a perfect copy of some complex curve, but you were only allowed to look at one single point on it. How could you possibly do it? Well, you'd start by building a polynomial that has the exact same properties as your curve, right at that specific spot. And here's how we do it step by step. First, you just make your polynomial touch the curve. Okay, they have the same value, that's a good start. Then you match the slope, that's the first derivative. Now your line is tangent, getting better. Next, you match the curvature, the second derivative. Now your approximation really starts to hug the original curve. You see where this is going? The more derivatives you match, the more our simple polynomial becomes an identical twin to the complex function, at least around that one little point. This whole process of matching derivatives isn't just some random idea, right? It has a formal name and a very specific recipe that mathematicians have perfected over the years. And that brings us to our next section. And here it is, the Taylor Polynomial. This is the master recipe. It's a formula that tells you exactly how to take the value, the slope, the curvature, and all those higher derivatives from one single point and then combine them perfectly to build the best possible approximating polynomial. This right here is the blueprint for your calculator's trick. Okay, but wait a minute. This is the most important question, isn't it? For science, for engineering, or even just for your finances, close enough is not good enough. We need guarantees. How does the calculator know its approximation isn't off by some tiny but potentially catastrophic amount? The answer lies in another brilliant piece of math. Now, don't worry about the crazy-looking formula you see here. What's important is its name and what it does. It's called the remainder estimation theorem, and you can think of it as the calculator's built-in quality control check. So, this remainder, it's literally what's left over. It's the error, that tiny little gap between our simple polynomial and the real complicated function. The power of the remainder theorem is that it lets us calculate the absolute maximum size of that gap, so we can make absolutely sure it's smaller than any tolerance we could possibly need. Okay, the theory is fantastic, but let's actually see the system in action. Let's put on our engineering hats for a minute and use this tool to compute something with guaranteed precision. All right, here's our mission. Calculate the sine of 3 degrees. But we have a very strict requirement. Our answer must be accurate to at least 5 decimal places. No guessing allowed, we need to be certain. So here's the crucial point. We don't just start building our polynomial and hope for the best. Nope. We start with that quality control check. We use the remainder theorem to ask a very specific question: how many terms, how many derivatives do I need to include to guarantee my error is smaller than 0.000005? And after running the numbers through that quality control formula, the math gives us a definitive answer. To guarantee the precision we need for the sine of 3 degrees, our polynomial has to be built using terms all the way up to the 10th power. That's our magic number, 10. And this just beautifully illustrates the payoff. We construct that 10th degree polynomial, we plug in our numbers, and after a series of simple multiplications and additions, boom, out pops the answer, 0.05234. And the best part? we know with mathematical certainty that this is correct to 5 decimal places. We've literally tamed a complex function with simple arithmetic.
And that's really the heart of it, isn't it? We've taken something conceptually abstract, like a sine wave, and we've transformed it into a set of instructions that even a basic calculator can handle with total ease.
So, the Taylor series is this incredibly powerful all-purpose tool. But you know mathematicians, they're always looking for clever shortcuts to make things even faster. You'll often hear about something called a Maclaurin series. It's not a totally new concept. It's really just a special type of Taylor series where we've chosen a very specific, very convenient point to center our approximation around, the number 0. So why is centering at 0 so great? Well, because calculations involving 0 are just easy. This makes the Maclaurin series the go-to default recipe for approximating fundamental functions like e to the x, sine, and cosine, where their behavior around 0 is simple and really well understood. Now, let's be honest, the hardest part of building these polynomials is often finding all of those derivatives. It can get messy really fast. And that's why mathematicians have developed entire toolkits of shortcuts, like the Leibniz Theorem shown here, which gives you a recipe for handling even more complex functions to make the whole process much more efficient. So the next time you tap a key on your calculator, just take a second to appreciate the elegant secret that's hiding inside. It isn't magic, it's the profound power of approximation. It's this core idea that we can understand, predict, and calculate the most complex things by starting with the simplest possible building blocks. And that really makes you wonder, doesn't it? What other complex problems in our world could be cracked with a similarly simple, elegant approach?